All right, here's our set one free response questions. I have not yet completely solved these, so I don't exactly know how they're going to be. The only things I know is that I saw an experimental design question on that, which I'm not looking forward to, but let's just go ahead and get started. You've got some sort of like potential map here with a charged rod as well as a sphere. Calculate the absolute value of the through the Gaussian surface whose cross section is the negative 20 volts equipotential line. Uh, okay, that's going to be fun because flux is just equal to Q enclosed over epsilon naught. Uh, yeah, and that's going to be 2 times 10 to the negative ninth coulombs over 8.85 or 6. I think it's 5, 8.85 times 10 to the negative 12 for epsilon naught. So that's going to give you 2 divided by 8.85 times 10 to the third power. The units of this are field times area. So that's newtons times meters squared over coulombs then. Electric field times area then. Yeah, there you go. I'm gonna be completely honest. I don't really want to try to work that out on my calculator. But I guess I can, just so you guys have an idea if you got the correct answer or not. But I think the important thing is like the actual process here. But if you're curious, it's 226, 226 newtons times meters squared over coulombs. All right, let's move on to the next page. All right, positive test charge is now placed and held at rested position C, which is along that same equipotential. An external force. Oh, geez. Okay. All right. Let me grab my paper copy real quick because I'm going to need to refer to the picture. All right. Got my paper copy here. All right. So it's moving from C to E to D to A. And then it's held at rest momentarily at each position. All right, absolute value of the work done. Okay, that makes sense. You have to exert some force in order to, because the sphere is going to be negatively charged, so you have to exert some force and therefore do some work to move it from C to E. Draw a bar to represent E to D and then D to A. And it should be proportional. Okay. Well, from E to D, the work done is going to be 0 because you're going along an equipotential, and therefore there's no work done. You're going to end with the same energy that you started with. Going from D to A, you're going from 0 volts to 30 volts, and so your potential difference there is 1.5 times the difference from C to E. So the bar is actually going to be filling up the entire graph then. All right. So it's going to be all 6 bars worth of this, and trying to color this in is going to be a pain. So there you go. All right. Again, the reason why is because your change in potential is 30 volts in the last column. It's 20 volts in the first column. And change in potential energy is given by Q times delta V, change in voltage. You have 1.5 times the amount of voltage change, potential change rather, potential difference, and therefore 1.5 the work done, 1.5 times the work done. Calculate the approximate magnitude of the electric field at position B. Okay, so we're given our picture on the previous page. To calculate the approximate magnitude of the electric field in position B, I think all we really have to do is just use the equation that relates that to potential. On your equation sheet, you're told that E is equal to negative dV dx. But since we don't have V as a function of X here, I think we're just going to have to instead treat this as negative change in potential over change in X. So 2 points that I want to use then. Let's go ahead and head over to the figure right here. Let's go ahead and actually use this point right here and this point right here, I guess. Yeah, I don't exactly know. I guess those 2 points work fine. The distance between those is approximately 0.4 meters. So you get a negative 10 over 0.4, which is equal to 10 over 2/5, which is going to be 25 newtons per coulomb then. So the electric field should be approximately 25 newtons per coulomb. Yeah. All right. The positive test charge is now placed at position D, and then it's released from rest. Indicate the direction of the net electric field or force immediately after it is from rest. So it is going to be directly towards the sphere because the sphere is negatively charged. All right, this is actually super easy to describe as well. So it is going to be directly towards the sphere. I'm just going to use text for this because you can't use equations. This kind of smacks of physics 1 style problem. But since the test charge is positive, it attracts toward the negative charge, the sphere, which is negatively charged. Actually, now that I think about it, no, it's not going to be directly towards it. Yeah, no, my apologies. It's not actually going to be directly towards the sphere because there's also the rod that has a positive charge density as well. So I think what's actually going to happen is, ooh, this is weird because if you go back to the picture, right? Let me just erase all of this here. If you go back to the picture here, you place a test charge at point D. What's going to happen is it's going to actually experience two forces. It'll experience a repulsive force from the rod, and then it is going to experience an attractive force towards the sphere then as well. If you add both of those together, my guess is that that should end up just causing it to be directly, it should end up probably being directly upwards, so plus y direction. But in terms of thinking about how we can prove that, my guess is that it's definitely going to have something to do with the spacing between potential lines, because you can see that the lines are closer on the left side of the sphere than they are on the right side. So you have a stronger field over here. The field is supposed to point. Oh, yeah, actually, that makes sense because the electric field lines are supposed to point normal to the equipotential surfaces. It has to be straight up then. Yeah. Okay. Yeah. Whew. Okay. There we go. There's our reasoning, actually. It is going to be plus y. Sorry about that. Again, I'm actually going to these questions, all of the E and M ones, almost completely blind. So forgive me if I do actually change my answer. So electric field, and therefore electrostatic force, must point normal to an equipotential surface. Since the test charge attracts to the sphere and repels from the rod, vector addition gives us a net force closer to plus y than negative y. There we go. Okay, that's good enough, I think. All right, let's move on. Oh no. Okay. Using, dang it, we're still not done with this question. This is long. All right. You remove everything. You have rod, and the rod is held at rest. Position P. Why would you not show position P? It's on the x-axis. Okay. All right, this is not too bad. Using integral calculus, derive the expression for v of p provided. That means we cannot use Gauss's law for this as far as I'm kind of thinking about, but I don't think that we really need to, because we could just say that Vp is equal to integral of the Coulomb constant, right, multiplied by dq over r. And so if I pull out the Coulomb constant, right, which is k, then dq is going to equal lambda dr over r. And so what we can say is, you can say actually that r is going to equal xp minus 4L then. Because that means that the closest distance, let's see, so lambda, so r is actually equal to, okay, sorry. Let's say, for example, that point P is located at 6L right here. Then the closest distance is going to be 2L, and the farthest distance away between the rod and point P is going to be 6L then. So that would mean that R has to equal XP minus 4L then, because therefore dr is going to equal dxp then. All right, so lambda dxp, and what you're going to have then is the I don't like doing that, actually. You know what? Get rid of all of that. Sorry, let's just keep this in terms of r, which is the distance between point P and the rod then. So the distance between point P and the rod then is going to be xp minus 4L to xp then, because the left end of the rod is at 0. Okay, that's easier. So you get k lambda natural log of r, where r goes from xp minus 4L to xp, right? Okay, that's much easier. I don't know why I was thinking to change this in terms of xp. You could do that if you wanted to, but I really don't think it's worth it, because you don't know where xp is actually located. So there we go. All right. I don't know if I'm just tired or what, but I feel like I would have just solved it in terms of r normally. But anyway, all right, sketch the component of the electric field in the region from 4L to 12L. Well, we can do that because we know that E is equal to negative dV dx, right? And okay, that's fun. So you get that that's going to be equal negative k lambda times 1 over the stuff inside of the natural log. So 1 over that is going to be xp minus 4L over xp times the derivative of everything inside. Okay, really? Times the derivative of everything inside. So you're going to end up with, if you use the quotient rule, you're going to end up with that on the top of the quotient rule. And then on the bottom, you're going to end up with xp minus 4L all squared. All right. Yippee. Okay. That just sucks. Negative k lambda times, well, those are going to go away. So you get 4L on the top, and then you get xp minus 4L squared. Okay, whatever that electric field is supposed to look like. That's like a 1 over x cubed at very big X. That's like a shifted 1 over x cubed, something like that. Yeah, it's going to go to infinity at 4L, obviously, because at that point P is right there, right at 4L, and so the denominator blows up. So I don't know, something like that. Yeah. Good enough. It's concave down. It approaches 0. Right. And I've shown my work for it. What more do they want? Okay. Whatever. All right, let's move on. All right. Now we have our circuits question. The students have access to a voltmeter that can describe potential difference as a function of time, and you're required to measure a quantity that decreases with time to determine R? Well, the potential across the resistors is going to increase as time goes on, and the potential across the inductor is going to decrease because the inductor is going to act like a wire as time goes on. So therefore, the place that we would put our voltmeter to measure a quantity decreasing with time is in parallel with the inductor to measure its voltage. Describe a procedure, oh no, to graphically determine the experimental value and provide enough detail so that a student can replicate the experiment. I hate these ones. All right. So you know the inductance and the voltage then. So what you're going to want to do is you're going to want to what we know is going to happen is since this is an RL circuit, you're getting exponentially decaying stuff. So what you're going to want to do is you're going to want to close the switch and start your timer. Um, and then um, And then what you're going to want to do is once the voltage has reached an approximately constant value after some long time. Actually, no, you don't need to do all that. Actually, what you need to do is once the voltage has reached half its maximum value, from when you started your time, start recording data rather, not your timer. Start recording data with the voltmeter. Right, so when you started your recording of data, right, once the voltage has reached half its maximum value, you can stop recording. And then what you can actually do is, oh, okay, actually, we're gonna have to graph some stuff. So no, I'm actually gonna go back to what I was gonna do originally. Sorry, since we have to actually graph some stuff. Once the voltage has reached approximately 0, stop recording data. All right, and then yeah, and then I guess in part B, it's telling you how you would graph it. So what I'm going to do is I'm going to graph voltage across the inductor as a function of time. All right. Okay. Actually, not voltage as a function of time. I'm actually going to graph natural log of voltage as a function of time. The reason why is because the voltage across the inductor should do something along the lines of V of t is equal to a battery voltage, because all of that voltage should be across the inductor to start, e to the negative t over tau, right? Where tau is like your time constant that depends on the resistance. And so therefore, natural log of V of t over E is actually going to equal negative t over tau. And then you can use like the slope of that graph to actually help you find the resistance then. So not just natural log of voltage, but instead of just natural log of voltage, let's do natural log of voltage divided by natural log of voltage divided by epsilon. So let me actually change that in my procedure. Natural log V of t over, not epsilon, script E. There you go. All right, label the quantities. That'll be natural log V of t over E. And then you have t right here. And then what you would expect is you would expect this graph to actually look like a we can do negative, I guess, too, sure. Because then in that case, you're going to get something that looks along the lines of that. Sure. And the intercept should approach 0. It's not actually going to be 0 because V. Actually, no, it will be. Yeah, never mind. Okay, that's fine. Yeah, this is good. It should just be a straight line then. You can probably see that from the equation that I wrote up top. All right, describe how the information could be used to calculate R. Well, the slope is going to equal negative natural log of V over E divided by T, which is going to equal 1 over tau, which is going to equal R over L. So therefore, R is going to equal L times the slope of our graph then. So I'm making use of the time constant for an RL circuit to help me solve for the resistance. And we do know the inductance, so we're all good. All right, I hate that question. All right, okay, here we go. There's our derived but do not solve a differential equation. Nice. I actually kind of expected something like this to show up this year. So that's, I guess, reassuring that, all right, do not, that can use to solve the current at time t after the switch is closed. You have to use Kirchhoff's loop rule. It tells us that. That's good because what that means is battery voltage minus the voltage across the resistors, right? Minus the voltage across the inductor should equal 0. So you could create a closed loop with either resistor actually, and you would get E minus I times R minus L di dt is going to equal 0. However, what I want to actually do is I do want to actually create one with equivalent resistance here. I want to kind of merge those two resistors into one. The equivalent resistance is actually just going to be R over 2 in this case because they're both in parallel. So you get E minus I R over 2 minus L di dt should equal 0 then. All right, there you go. All right. You might be wondering why R over 2 and not just R, because you could create a closed loop with one resistor, the inductor, and the battery. The reason why is because that R over 2, the fact that you have two resistors in parallel, that's actually going to affect the current because it's decreasing the equivalent resistance of the circuit then as well. So you have to include equivalent resistance for that in order to ensure that you're getting the correct maximum current and the correct trends in terms of how fast things will charge or discharge then as well. So, all right, that's all good then. Okay. After reaching steady state, you get the absolute value of the potential difference is that you replace the original inductor with a new inductor that has non-negligible resistance. After a long time, the value of the potential difference across the new inductor is delta V2. Indicate whether it's greater than, less than, or equal to. Okay, I am always struggling with these on circuits questions, these kind of comparison ones. So you're going to increase equivalent resistance, which is going to decrease the current. And there, but since you're still going to have current going through the inductor, you can find the potential difference across the inductor by using V is equal to I times the inductor's resistance. Whereas in steady state, if the inductor has no resistance, it has no voltage at steady state. So V2 has to be greater than V1 for that reason. So let me just go ahead and type that out. V is equal to IR, right? So even though an inductor with resistance increases equivalent resistance and decreases current through the circuit, V is equal to 0 in the first case, but it will be, and it must be non-zero in the second case. Yeah, there you go. So it has to be greater in the second case. All right, going back to part C, actually, because something I was thinking about, you actually do indeed have to use equivalent resistance and not just one of them. The reason why is because the current through just one resistor would not be equal to the current through the inductor then. So that's why you have to use R over 2 instead of just R then. Sorry, just a note that I kind of came up with. All right, let's go on to question 3 then. A wire is connected to a resistor, blah, blah, blah. There's an external force so that it always moves in constant speed. Then enters region 1. Then yeah, you have some boundaries, cool. That enters region 2 with two different magnetic fields that are parallel but in opposite directions. And then point S is the midpoint. Okay. All right, I have a feeling I'm going to need to refer to this picture. Good thing I still have my paper copy here. Let's go ahead and move on to the next page then. All right. Oh, okay. Sketch the magnetic flux as a function of x. Okay, that's just great. All right. Okay, sketch the magnetic flux. Well, your magnetic flux as a function of x, magnetic flux goes like integral of b dot dA. And as the bar is going through, the flux is only changing in the x direction and not in the y direction, and the field is constant. So what you're going to get is you're going to get b times the height of the rod, which is 2L, multiplied by how much of the rod is actually included in there. So from 0 to L, you're not going to have any flux because there's no field. If you go back to the picture, you'll be able to see that. And I'll show you guys in just a minute. Then from L to 2L, you have part of the bar actually starting to go into that region with field going out of the page. Into the page. So therefore, you should get it's proportional to negative x for both of those parts. And that's going to be constant until you get to 2.5L. That's the end of region 1. And then the magnetic field is going to end up changing. Region 2 has the same magnitudes of magnetic field as region 1, but half of it is pointing in the opposite direction. So what's going to happen is as you go from 2.5L to 3.5L, you're going to have the field actually changing half as fast. So it's going to go something like that. No, it should go down to 0 though, because once the bar is from 2.5 to 3.5L, you have the same amount of magnetic field. So it has to go down to 0 once the entirety of region 2 is contained within that wire. So therefore, should it go down at the same rate? No, it shouldn't. Because if you go back over here, if the rod is located right here, for example, between 2L and 3L, right, you have like, I would say, I guess about 3/4 of the flux. And then when it goes from 2.5L to 3.5L, you would have no flux in it. I hate these questions. All right, so once the bar gets past 2.5L, the flux does start going towards 0. It has to be 0 when you get to... It has to be 0 when you get to 3.5L. And then as you're going to 4.5L, it has to remain 0. It's going to remain 0 between 3.5L and 4.5L. That part I'm sure about. But as you're going from 2.5L to 3.5L, you're increasing the flux out of the page, and you're decreasing how much of it is going into the page. Both of those are happening like x. Both of those are proportional to x, so it is going to be the same rate. Okay, so yeah, that's what it should look like then, is same rate of change between L and 2L and 2.5L and 3.5L. Reason being, and hopefully I can explain this well. As the bar is going from 2.5L to 3.5L, as the right side of the bar, that is going from 2.5L to 3.5L, you're losing the flux from region 1, and that's proportional to x, how you're losing it. But then you're gaining the flux from region 2, that's also proportional to x. Actually, wait, no, because then the amount, the total change in flux that you're getting in region 2 should be, yeah, no, that works, because the total change in flux from region 2 is going to be 0, because you're enclosing equal parts field going out of the page and into the page then. Okay, no, that works out then. So the only thing that matters between the right side of the loop going from 2.5L to 3.5L is the loss of region 1's flux then. Okay, I'm confident with my answer now. All right, okay, at the instant when point S reaches 1.5L, indicate whether the current is going to be clockwise, counterclockwise, or 0. It is induced current. When you reach 1.5L, you're increasing the flux into the page then. And so what that is going to mean is that you get a counterclockwise induced current then. So it's going to be counterclockwise by Faraday's law. So Faraday's Lenz's law, actually. Lenz's law states that the induced current resists the change in flux caused by the movement. Since the change in flux is into the page, negative z direction, the induced current is counterclockwise to generate a magnetic field out of the page, or a magnetic flux out of the page, if you will. Yeah, there you go. All right, so I like using Faraday's law, nice and easy. All right, derive an expression for IR. Explain how that is equal to, okay, so that's not too bad, because what we have to do to derive an expression for IR is we do have to find induced current. To do induced current, you have to use Faraday's law. So IR is going to equal the induced voltage divided by resistance, which is going to equal the absolute value of d phi dt then. D phi dt over R. As we stated in the previous case then, the flux itself is actually going to be like field multiplied by area. So B times 2L times X, that's how much of the magnetic field will be enclosed. So you get that divided by R then. So if you take all of that, B and 2L are constants, so you get 2BL over R dx dt, which is equal to velocity then. So so you do get that IR is going to equal 2BLV over R. All right, there you go. Derive an expression for the power dissipated. Power dissipated, not too bad. It's just I squared times R. Yeah, so that's going to be what? 4B squared L squared V squared over R then, right? All right, let me make sure I did my math right. Yeah, that looks good. Sorry, not IR. That's going to be power. There we go. I squared times R then. All right, I think we still have some more. Yep, we do. Oh my goodness, these questions are so long. All right, I feel like I've been working on these for ages. Okay, total energy dissipated is E original. The vertical boundary now shrinks. Okay. And then it moves with the speed again. The total energy is E nu. So greater than, less than, or equal to. Okay. Total energy dissipated. So you have to figure out how the power dissipated is going to change. And let's see. So So what happens is if we go back to our graph for flux, I'm gonna redraw that graph for flux then. What that looked like in the original case was along the lines of this. Okay. Now, in the new situation, you're shrinking the vertical boundary of region 1, and so it goes to 1.5 L now. So what's going to happen is you're still going to have the same trend in flux from 0 to 1.5 L. It's just once you reach that, uh, you are going to end up having you're going to end up actually getting the current to go down to 0 sooner. By the time you reach 2.5 L, your current should be 0 then again. So what's actually happening here is you're going to have an induced current for less time, it looks like, because as the bar goes from L to 2L, as the right side of the bar goes from 1.5 L to 2L, you're going to have a constant flux then. So what the new flux is going to look like as a function of time is you'll still have a trapezoid, but you'll have that trapezoid for less time then. You'll have that trapezoid for less time. The flux is going to be changing for less time then as well. So I do believe that you're actually going to have a lower energy dissipated. So the reason why is because the flux changes at the same rate, but for less time and over less distance. Therefore, the induced current is present for less time. So there is less power dissipated and less energy dissipated. Okay. Original magnetic fields are modified. Oh no, there's a triangle. Sketch the induced current. I don't want to. Okay. All right. Flux as a function of time, B times A. Area of a triangle is 1/2 base times height. Oh, but the flux, oh, this is no fun because the height is actually changing as time goes on too, because you're enclosing less of the triangle as point S gets closer to the field compared to the left side of the triangle. More of that triangle is entering the field as the left side of the triangle. So you get more flux. Oh man. 1/2 base times height for your triangle. Both of those now are going to vary based on x. Base is still going to be x. And then the height. Oh, similar triangles. Height is going to have to be 2x then. That's just cruel. These are similar triangles, so the height has to be 2x. So the flux is going to be bx squared then. All right, so therefore the induced current, because the voltage is going to be d phi dt, which is given by 2bx times dx dt, or 2bxv then. All right, so that's just going to be linear from 0 to 3L then. All right, so let's just sketch it. There you go. All right, that's the end of this set, guys. We're almost there. One more set to go. I don't know if you guys can tell, but I'm tired. These questions are long. The mechanics ones were not too bad. They were just tedious, but these ones I feel like are long, and honestly, I am kind of struggling a little bit with these right now. But Anyway, I hope you found this helpful. I'll see you guys in the next set. Thank you for watching.